quick. We'll see if we can combine everything. Let's say this went 75 degrees in 1/2 of a second. So circle rotates 75 degrees in 0.5 seconds. A, what is period of rotation? B, what is angular frequency? Of the circle? And then C, what is frequency? So take about 5 minutes, see if you can get those real quick, okay? And you can work with the person next to you, discuss it. If you disagree, convince your partner you're right. Just like how this is written. So you just have to
How did you get the omega again?
And then you had a comma with the T over.
Omega is the angle over t. So we have
Oh,
to
you're
find
just,
an angle. So
you're just solving for T. Okay, yeah.
delta over.
And this is omega down
And
here, right?
we
Yeah.
need to
Okay,
change.
just checking.
We need to change the delta into. I know. So 2 pi over 2.3.
Do we have to do it in radians?
What is the angle? Oh, that's really similar.
Are you good?
For A, 2.4, and then 2.62. Yeah, because I just wanted to know. Is the frequency 1 over big T?
Yeah.
you have a meet yesterday?
Well, yeah, but I didn't hear him.
Because that's how you eat.
You did this.
I do this one already.
Really?
Yeah.
How did it go?
It was well. We went one, 5, 4, 5, 6.
Wow.
We were racing against them for college college garden. College. It wasn't very good.
I was like, yeah, you guys are balling.
Okay, so what was the period of rotation?
2.4?
1 second.
Okay, what's the angular frequency?
2.62. What is it?
Do you have to change it to radians first?
What's the? What do you?
Radians per second?
Oh, is that what you?
For this one, for the unit?
Yeah,
this one?
unit.
Yeah. Radians per second. Radians are dimensionless. So actually, it's standard practice to just write this as seconds to the -1.
So it's the same.
It looks like
So
a
it's-
So it's the
hertz.
same 1/7.
So it's not hertz?
Hertz is total rotations per second,
But it's,
and same units,
yeah, so they're both
but we
inverse
call it a
seconds.
hertz per frequency.
Okay.
I said you have to change. You have to change the degrees to radians first before you do any of the other stuff.
Yes,
Pretty much.
yes. So we started out with S is equal to R theta. That was the basis that we used to get that the angular speed is equal to R omega. And that the speed is equal to R theta. So we have to start with all the angles in radians. And that'll probably always be the case with circular motion. Make sense?
So it's 75 over 360 times 2 pi, right?
No, 75. You're changing 75 into radians first.
Yeah.
So you get 5 pi over 12, and then
It's 2 pi over 360 times 7. You're 75.
yeah, or pi over 1.
You want
Right,
the
right,
degrees
right,
on the
right.
bottom so it cancel out.
Times 2 pi.
And then what's the frequency of the rotation? What do you get for this?
0.42.
0.42
So that means-
hertz. And what you did was you just did 1 over that.
Oh,
Let's go see how this works. So this is all correct answers. Period of rotation is T. Well, it's most convenient probably to write T is equal to 2 pi over the angular frequency. Angular frequency then will be what we'll solve for first. That is just the angle
over time.
divided by the time. So the angle it went through was 75 degrees in half of a second. We already found out that the angle is 5 pi over 12, if I write it in radians, over half of a second. And so that would be 5 pi over 24. Wait. Over 6. 5 pi over 6.
Yeah, it's 5 pi over 6.
6.
No, yeah.
Yeah, you're right.
It is?
Yeah.
Oh yeah,
It's
that's W.
twice as much
Yes,
as-
it is.
Okay, so that's the angular frequency, and then we can do this. Then I take, for the period, I take 2 pi over that. That should give me 2.4 seconds. And then I take frequency is 1 over period, and that should give me that. Okay? So hopefully all this terminology is kind of becoming a little bit clear. There's a fair amount of terminology here. All right, you ready to be introduced to something? Sure. This is the terminology. I don't think we've really covered a whole lot of new stuff. This next thing will hopefully let you do the last problem. Okay? So, oh, by the way, there's the rate of change of angular velocity over the time that it takes. That would be the final angular velocity minus initial angular velocity over t, the time it takes to change. This is called angular acceleration. symbolized by a little Greek letter alpha. Okay. So that might be necessary. Some clue. All right, let's go ahead and let's look at what happens to a point on the edge of the circle. Let's look at its velocity vector at two different points, okay? I'm going to make the angle here a little bit smaller. So we'll look at two nearby points. And then look at its angular velocity at two nearby points. So we'll look at this point and this point. So this thing's rotated. Okay, so this is initial position. And then this would be the final position. I'll just call it RF here, the final position. Velocity, gosh, shoot, R initial, R final, I'll write it like that. Velocity is always going to be tangent to this circle. So what that means is that like the velocity here will be like this, right? So if I were to draw it, I'd have a velocity vector here like this. I'm going to call that the initial. Because this point's moving in that direction at that time, right? This, if I go over to here, this velocity vector here, moving a little bit like that, right? V final. If I were to put these velocity vectors side by side, you know, my V initial would look like this. My V final would be rotated a little bit like this.
But they both do the same speed.
Yeah, we're assuming same speed, so it's just a constant angular speed. The key, one interesting thing is that actually the change from the final vector to the initial vector, the little change in that vector points this way. And if I were to draw that on there, it looks like it would point towards the center of the circle. That's actually what happens. The condition for an object to be moving around in a circle at a constant speed is that it's actually accelerating. Because the direction of the velocity vector is constantly changing. So that means that there's an acceleration. The direction of that acceleration is towards the center of the circle. And that's just the condition for an object to be moving in a circle. We actually know what the magnitude of that acceleration is. I'll just give you the formula for that. The magnitude of the acceleration, we call it centripetal acceleration. This is for an object to be moving in a circle. I'm writing a little r here to indicate that it's something to do with radius or circles. It is actually v squared divided by r, the radius of the circle. Or because omega is v, because v is equal to r times omega, if I put that into here, I would see that that this could be written as r squared omega squared over r, which is r omega squared. So this is the condition for the magnitude of the angular acceleration. We didn't derive this magnitude, but we did sort of give an argument for the direction. The direction points towards the center of the circle. So real quick, here's what we will do. Just give you a taste of this. Say I have a merry-go-round, and it's moving with a angular speed 0.5 radians per second. And it has a radius of 2 meters. If a person is on the edge of this playground, of this one, and I do a big person, we'll say that the radius of this person's at 2 meters. So maybe here, 2 meters. We can then find what the forces need to be to keep it in that direction, to keep it moving like that. So the sum of the forces on the object have to equal MA. And we know that A, if it's moving in a circle, will be pointing that way towards the center of the circle, and it will have this magnitude. So that means A, let me draw A. A will be pointing in that direction, and it has to have this magnitude. That's what it means to be in circular mode, to be moving in a circle. So whatever the forces are, they have to add up to that to keep it in a circle. And, well, I guess I'll leave it at that for now. We'll do a lot of examples starting on Monday. Yeah, it's actually fun.